Okay, so now we understand the contact models. We know what form and force closure are. Okay, so now let's get to the heart of the question. Okay, when is an object completely immobilized? When is an object stationary? Okay. All right. So for this, let's just look in general three-dimensional case. All right, so we have a bunch of, say, forces being applied to this rigid body. Okay, so let's call the forces F1, F2. So these are now, okay, bunch of forces. All right. So when is the object stationary? Okay. When is the object stationary? So when is the object stationary? It doesn't move. Okay. So what do you think? Well, let's see. How many are familiar with the concept of static equilibrium? Static equilibrium. Okay, you know this. Okay. The sum of the forces have to be 0. Okay, so sum of the forces have to be 0. Okay, is that enough? Is that enough? So here's an object. Here's a force applied this way. Here's a force applied that way. Okay, this force plus that force. Okay, so this force plus that force, they sum to 0. Okay, but if you apply force this way, force that way, it could rotate. Okay, so we don't want rotation. So we also need one more, and that is the sum of the moments also have to be 0. Okay? All right, so to describe a moment, we need, let's attach a reference frame. Okay, so this vector here is R1. This vector is R2. Okay, so it's from the origin of this reference frame to the point of contact. That's how we're going to define the Ri's. Okay, so we need these two equations to be true for this object to be completely stationary. Okay, and this is just nothing more than the idea of static equilibrium. Okay. All right. So turns out this is the main idea we need, the main concept we need to answer our question. Okay. All right. Okay. So I think all the pieces are ready now. We understand friction models. We have the static equilibrium equations. Okay. So now let's answer our original question. Okay. So back to the first example. Okay, so let me draw this in slightly enlarged form. Okay, so there's my picture. Let me just make it a rectangle now. Okay, and I have a point contact, say here, here. Let me change the location a little bit. Doesn't really matter too much. Here, and say here. Okay, so I put the contacts in asymmetric locations about this picture frame. Okay. All right. Now let's add a reference frame in the middle. Okay. All right, and these are frictionless point contacts, no friction. Okay, so 4 frictionless point contacts, PCs. Okay. All right. So we also need some dimensions. Okay. Well, actually, let's say that the force applied at this contact, okay, frictionless. So that means forces can only be applied in the normal direction. Okay. So let's call this force F1. This is F2, F3, and finally F4. Okay. Okay. Some more dimensions. So let me call this distance L1. Let me call this L2. This will be L3. And finally, this will be L4. Okay, so here we go. We have 4 frictionless point contacts in contact with this picture frame. Okay. Now, suppose some external force is being applied to this object, okay, somewhere. Okay, so now let's ask ourselves, is this object stationary? Okay, so what do? Now we use our static equilibrium equations. Okay, so suppose external forces are applied. Okay. Then object is stationary when? Object is stationary if, okay, the static equilibrium equations we have the 4 forces plus external force, okay, that has to be 0, and the sum of the moments, right? So R1 cross F1, we have 4 of these. Okay, and then we have also the external moment plus R external, say, F external. Okay, this has to equal 0. Okay, so this is all we need to check. All right, so now let's check that. All right, so now let's write down the forces. So F1 is going to be what? It's in the minus y direction. Okay, so F1 is going to look like something like that, 0 minus x1. Okay. F2 is in the minus x direction, so it's minus x2, 0. Okay. F3 is in the plus y direction, so it's 0x3. And finally, F4 is in the plus x direction, so it's x4, 0. Okay, so that's what the components of the forces look like. And it's important to remember here that these x's are greater than or equal to 0. Okay, so why is that? Well, we're only going to assume that these things can push. Okay, they cannot pull. Okay, so no sticky stuff. You can't pull it. Only push. Okay, so let's write down these equations, okay, in terms of the components. All right, so the first set of equations, sum of the forces equal to 0, means add all these up, right? Plus external. So we have minus x2 plus x4. Okay, and then we have minus x1 plus x3. Okay, plus we have some external force in the x direction plus the external force in the y direction. Okay, so this has to equal 0. Okay. Okay, so that's this equation. Now let's write down this equation. Okay, so let's look at R1 cross F1. Okay, so I am going to assume that all of you know how to take cross products. Okay, so it's the right-hand rule, remember? So R1 cross F1. So let me walk over here, not too fast. So here's R1. Okay, so R1 cross F1. Right, so you take R1, which is that way, F1, you cross it in using your right hand. So that means the thumb indicates the direction. Okay, so the direction is into the board, which is the minus z direction. So call this xy. So, okay, so R1 cross F1 is into the board, minus z direction. The magnitude is, well, you can see that it's just going to be this force multiplied by L1. Okay, so R1 cross F1, we write down the components. It's going to be 0, 0, minus L1, x1. Okay, and you can find R2 cross F2, R3 cross F3, R4 cross F4, similar way. Okay. So let me just do a dot, dot, dot. All right, so if we calculate each of these terms independently, add them all up, what we'll get is, okay, let's make sure I do this right here. So we have 0, 0. We have minus L1, x1, and plus L2, x2, plus L3, x3, minus L4, x4. Okay. Equals 0, 0. And then we have the moment due to the external force here, right? So let me just call that minus m external z. Okay? All right, so here's a useful trick. In the plane, well, first of all, if everything is done in the plane, we don't care about x and y. These are always 0. Okay, so 0 equals 0 is not very useful, so just ignore. Just write down the z component. Okay, and now you notice some of these are minus, some of these are plus. Okay, it's useful to remember that moments that are counterclockwise, okay, are considered positive. Moments that are clockwise are, the sign convention is that they're negative. Okay, so F1 and let's see, F1 and F4 cause the object to rotate clockwise. Okay, so that's why there's a minus. F2 and F3 cause their object to rotate counterclockwise. That's why they're plus. Okay. Okay, so let's ignore the xy component. Just write this down. Okay, so now if we rearrange these equations, 1, 2, 3. Okay, now let's write them in a slightly more organized way. Okay, so we can write the equations in the following way. So we have 0, minus 1, 0, 1, then minus 1, 0, 1, 0. And the third equation is minus plus plus minus. So it's minus L1. Okay, so this times x1, x2, x3, x4 is equal to okay, I'm going to write this as just b1, b2, b3. Okay? So you can see that here b1 is just minus f external in the x direction, b2 is minus f external in the y direction, and b3 is just minus of the external moment. Okay, so here's our equation. And it looks, what? It doesn't look scary, right? Why? Because it looks like it's of the form ax equals b. Okay? So you spend at least a semester studying ax equals b. Okay? So you should probably look at this and say, aha, I know the answer to this. Okay? So it's so there you have it. Okay, this very practical question. Where should I put the nails? Okay, reduce this to a linear algebra question. Ax equals b. All right. So I don't know how many of you are excited about that. Not too many people are excited about that. Okay. Can we answer this question? Okay, so here's the question. Question is, so the statement. So the object. Okay, let's try it again. So if a feasible solution x, so x here is 4-dimensional. Okay, exists for now. This b1, b2, b3 are the external forces and moments. They can be arbitrary. They can be anything. Okay? So what we want is that a solution x exists for any arbitrary b. Any arbitrary. Okay? Then what does it mean? That means that we can resist any external force and any external moment. So the object is stationary. Okay? Object is stationary. Okay? Or more precisely, it's in form closure. Okay? We have form closure. All right, so ax equals b. When does a solution exist? Well, if a were square, that would be easy, right? Just see if the inverse of a exists, and if it does, then you have a unique solution. If a is not square, okay, you have to do a little bit more analysis, right? What sort of analysis do you have to do? Okay. Well, B has to be in the column space of A, right, in order for a solution to exist. And if it does exist, then you have to see, is it unique? Is there more than one solution? Okay. Feasible. Okay, feasible. All right, so what are the requirements on X? Okay, so for our problem, negative. Okay, so this is the big difference from what you learned, okay, in linear algebra. You didn't worry about this. Here we have to worry about this because our fingers cannot pull, they can only push. Okay. So unfortunately, we have to sort of start over. Okay. We can't use the old result from linear algebra. Okay, so as a good engineer, okay, when you see a problem that's kind of hard to grasp, okay, no pun intended, hard to grasp, what do? You try to simplify, right? Think of a simpler problem. So if this is a three-dimensional problem, maybe think of a two-dimensional problem, okay, that has all the essential features, okay, and then try to understand what's happening in the simpler version, then bootstrap to the higher dimensional version. Okay, so let's do that. So let's consider a easier version. Okay, so let me consider matrix A of the form 1, 0, 0, 1 and minus 1, 1. Okay, so here's x1, x2, x3 equals b1, b2. Okay, all right. So now let's see if apply the same question to this equation. Okay, and here we want x1, x2, x3 also to be greater than or equal to 0. Okay, so does a solution exist for arbitrary b? Okay, now I've been emphasizing this throughout the course. Okay, try to think geometrically as much as possible. Okay, so for this case, let's continue that philosophy. Okay, let's think of these as vectors, as column vectors. Label them A1, A2, A3. Okay, and this will be my vector B. Okay, so another way to write AX equals B here is to say that B is just the linear combination of x1, x2, and x3. Okay, so in other words, x1 times A1 plus x2 times A2 plus x3 times A3. Okay, so this is equal to B. Okay, so we're just adding three vectors weighted by x1, x2, and x3. Okay, so here we go. So here's vector. Here's vector A1. Here's vector A2. And here's vector A3. Okay. All right, so there are my three vectors. Suppose my vector B is this. Okay. Now, is there a solution? Okay. x1, x2, and x3 for this given B. Okay. So what we're doing here is we're stretching A1, stretching A2, stretching A3, adding the three together, and seeing if that can somehow match B. Okay. And now from this picture, it's pretty clear that's impossible, right? The only linear combinations of A1 and A2 and A3 all lie inside here. Okay? So you can't reach this vector. Okay? So for this case, it's pretty clear no solution. Okay? Now, what if I changed A3? So A1 and A2 are still the same. Okay, but now I change A3 to be that. Okay? Then in this case, it's pretty clear, I think, that there will be a solution. Okay? So solution exists for all B. Okay, now why is that? What's the difference here? What's the difference here? Okay, so here's the difference. A1, A2, and A3, if you look at the way they span the space positively, okay, so it's called the positive span, it spans the entire plane, R2. Okay? In this case, okay, if you look at the positive span of A1, A2, and A3, it's just inside here. Okay? It can't go outside. It's only inside here. Okay? So that's the difference. Okay? But that's kind of sort of hard to, it's not a very compact way to characterize that. Okay? So what we can do, another way to think about that is to look at the triangle formed by A1, A2, and A3. Okay, so there's a triangle. Okay, so notice that this triangle does not include the origin. Okay, whereas if you go over here, okay, the triangle includes the origin. Okay? So, okay, origin is inside this triangle. Okay, over there, the origin is outside the triangle. So that seems to be the fundamental difference between these two situations. Okay? So this is what we want. Okay, so the origin, we want the origin to be in the interior of this triangle. Okay, so now let's go back to the example. Okay, so we'll wrap up here now. So our original A, gosh, I wish I had not erased that. 0 minus 1 minus L1, right? And this was minus 1, 0, L2, so 0, 1, L3, and then 1, 0, minus L4. Okay, so that was our matrix. That was our A matrix. So here's A1, A2, okay, so on. Okay, so now let's apply this reasoning to this three-dimensional example. Okay, so now we have, before we had a two-dimensional drawing, now we have a three-dimensional drawing. Oh, let me draw it. It's better to draw it this way. Okay, so here's my x, here's my y, x1. No, sorry, hold on. Okay, x, y, z. Okay. Okay, so let's draw A1. A1 is 0, minus 1, minus L1, so probably around here. So that's my A1. Okay, and then my A2 is minus 1, 0, L2. So maybe, I don't know, here. Okay, so this corresponds to point A2. Okay, A3 is 0, 1, L3. So 0, 1, L3. That'll be my point A3. A4 finally is 1, 0, minus L4. It's my A4. Okay? So now I have 4 points in three-dimensional space. Okay? So we can imagine these vectors, okay, like this. I don't want to clutter the picture too much, okay, but imagine these vectors here, like that. Okay? So the positive span of these vectors should cover the entire three-dimensional space. Okay? Another way to say that is that the shape, the volume, obtained by connecting these, okay, for so something like that. Like that, and I guess there's that, and there's also, there we go. Okay, so this is a tetrahedron. 삼면체, okay, tetrahedron. All right, so what's the equivalent condition? We want the origin to be inside the volume of this tetrahedron, okay, for this to be forced closure. Okay, so let's so if origin lies inside tetrahedron, then solution exists. Okay, we have form closure. Object cannot move. Okay, and we have form closure. Okay, if it's outside the tetrahedron, we don't have form closure. Okay, so you have to imagine, okay, this tetrahedron. You can sort of see it, okay. Practice drawing it, you'll get it. Okay. Okay, last case. So now let's get the final answer to our question posed at the beginning of the class. Okay, so suppose now L1, L2, L3, and L4 are all 0. Okay, now I told you that this is not good. Okay, let's see what happens here. All right. I'll take care of him after class. Okay, so if L1, L2, L3, L4 are 0, what happens? Sorry about that. Okay. If L1, L2, L3, L4 are 0, what happens to these points? These points all drop to the xy plane. Okay, so we get, so the tetrahedron now becomes a square. Tetrahedron now becomes a square. Okay. So now the question, is the origin inside the tetrahedron? It looks that way, okay. But in fact, the tetrahedron is no longer a tetrahedron. It's a square, okay. So it's no longer, it's a tetrahedron, okay. We need this to be a volume in three-dimensional space, but this is just an area. Okay? So no solution. Okay, so this is not form closure. Okay. Okay, so it's kind of a long journey. Okay. In the end, what do? We managed to reduce our original problem to a very geometric one, right? Is a point inside this tetrahedron or not? Right? Okay, so next time we'll give you a more precise computational test for this form closure. Okay, that's all. Thank you.